here. It's a great pleasure to have Professor Amir Yacoby from Harvard University here today. Amir is currently a professor in physics, in applied physics, and I think he's visiting professor at the University of Waterloo. Amir got his bachelor's degree in aeronautical engineering, master's degree in theoretical physics. Then he switched to experimental condensed matter. He got his PhD in 1994 from Weizmann Institute. He focused on coherence in quantum mesoscopic systems. Then he came to the United States. He did a postdoc at Bell Labs and worked on, I guess, one of the major efforts at that time was this cleavage over gross quantum wires and sort of really observing this Luttinger liquid physics. Sort of separating charge in the spin. That was a really cool experiment. Then he actually went back to Israel. He became a professor in Weizmann, and where he focused on imaging electrical charge with these SCT devices to locally look at the charge and the dynamics of the TLEC systems. In 2006, Amir became a full professor at Harvard University. Since then, that's sort of actually the time that I became a graduate student at Princeton and sort of been following Amir's work on many different areas on quantum computation, spin qubit, NV centers for quantum sensing, topological systems. I guess today we will hear about the mercury telluride story. Very amazing experiments, graphene, quantum Hall effect in graphene, interaction in graphene. I've been always enjoyed Amir's work, and at least when I was a student, Amir was known for doing the hardest experiments. So it's a great pleasure to have you, Amir, and sort of we will hear more about it.
Thank you very much. So thanks, first of all, Javad, for inviting me, and also Andy for giving me the opportunity to visit. And tell you a little bit about the work we've been doing over the past several years, primarily focusing at what I will call unconventional superconductors. And as you'll see, these superconductors open up some really exciting possibilities for exploring new types of particles in condensed matter physics and new types of order in superconductivity. So the type of unconventional superconductivity that I'll talk about today is one that arises because of incompatibility, largely incompatibility between superconductivity and magnetism. And so superconductivity and magnetism are perhaps the most well-known ground states in condensed matter system. I'll spend just a few minutes reminding everybody what these are and where this incompatibility comes from. So magnets, of course, we know exist for thousands of years, and they have several properties, one of which is spontaneous breaking of symmetry. The system, in principle, could order in a way that breaks time reversal symmetry, either a ferromagnet or an antiferromagnet, and it really took us a couple of thousand years to properly understand magnetism. We know that to understand magnetism, we need quantum mechanics. And the underlying principles that govern magnetism is a competition between kinetic energy and Coulomb interaction. For example, in a ferromagnet, the Coulomb interaction between electrons, because of the Pauli principle, is suppressed when the electrons have identical spins, because you cannot find them at the same location in space. So the Coulomb repulsion becomes weaker, and the system gains stability by lowering its Coulomb interaction. It pays a little bit of a penalty by squeezing the orbitals, and so there is a little bit of a penalty associated with the zero-point motion or kinetic energy, but in ferromagnets, Coulomb interaction wins and the system favors this ordered state. Antiferromagnets, it's exactly the other balance. If the system is forced to have opposite spins nearby, then now the electrons can easily spill over one on top of the other, thereby making their orbitals larger, reducing their zero-point energy, the kinetic energy, on the account of paying some Coulomb interaction, but in these systems, reducing the kinetic energy gains the system more energy, and they order in an antiferromagnetic state. Spin-orbit interaction will be important throughout this talk. I just want to point out that recently, over the past maybe 10 years, there are new types of magnetic systems that are not precisely ferromagnetic or antiferromagnetic. There are some kind of hybrids, chiral magnets they're called, where on shorter length scales the system looks ferromagnetic, but on larger length scales it actually looks antiferromagnetic. And the key ingredient that is responsible for generating these kind of patterns has to do with spin-orbit interaction, and this will be something that I'll talk about later in this talk. Superconductivity is a younger field discovered in the early 20th century and also has spontaneous breaking of symmetry. It's a little bit more of a subtle breaking of symmetry, which is called gauge symmetry. So what characterizes superconductors is that pairs of electrons condense, and they condense in a particular way in conventional superconductors, where pairs of electrons that have opposite spin and opposite momentum form a bound state, and these bosons then condense to form the condensate. And what characterizes the overall macroscopic state of this condensate is this order parameter, and you see it has an amplitude delta, but it also has a phase, and this phase is spontaneously chosen. So if you just take a chunk of superconductor, you can easily measure what delta is, but phi will be arbitrary. So similar to the magnetic system, this system has a lot of symmetries associated with the ordered state, in particular singlet superconductors. And when I refer to singlet superconductors, I refer to this, the nature of the pair wave function. It is basically very highly symmetric in the sense that the pair wave function is translationally invariant. There is no particular spatial order to this order parameter. It has also orbital symmetry. It doesn't matter how you look at this pair. It still has zero angular momentum, zero projection of its angular momentum, and it has no net linear momentum. Now, it's not hard to see that magnetism and superconductivity are incompatible. Superconductivity wants the spins to be opposite one another, and it's not enough that it's an antiferromagnet where there is time reversal symmetry broken. This really wants to be a time reversal symmetric state, whereas magnetism, for example, the ferromagnet wants the spins to be aligned. So these two states don't mix together, and in fact, the only place where there are some experimental indications of seeing coexistence of ferromagnetism and conventional superconductivity is usually just before superconductivity goes away. So you might ask, well, why would we try to mix these kind of things? And there's actually a good long list of reasons that one might be interested in trying to create superconductors that have a ferromagnetic type of order parameter. And one example is, for example, if the pairs of the superconductor were of the same spin, obviously this superconductor will not be as susceptible to magnetic fields as this one. This one really doesn't want magnetic field in it because it will break the pair. Another kind of interesting feature that you could have if you had a triplet superconductor is that you could send supercurrents that carry spin. So that could be really useful. For example, in spintronic devices, if you could send really large densities of spins dissipationlessly, this would be very useful. The topic that I'll mostly talk about today is that triplet pairing, or this kind of hybrid between magnetism or triplet order and superconductivity is going to be needed if you want to create new types of particles in the condensed phase, and these will be non-abelian excitations that I'll spend some time describing and show some pathways of how to realize these kind of systems when you try to mix a conventional superconductor with something that favors magnetism. Now, the difficulty with this kind of unconventional superconductivity is that nature is really unkind. It hasn't given us really a lot of examples where we have superconductors that are not singlet pairing. And the first basically theoretical works that tried to explore unconventional superconductors were by these four gentlemen, Fulde, Farrell, and Larkin and Ovchinnikov. Fulde and Farrell are from the west, and Larkin and Ovchinnikov from the east. So This is called the FFLO state in the west and the LOFF state in the east. But nonetheless, it describes the same phase. And the phase basically addresses the following very simple system. So imagine an itinerant ferromagnet where I have a little bit more spin-ups than spin-down. If one just looks at the Fermi surface of this material, one could see that the Fermi surface of the minority spins is small, and the Fermi surface of the majority spins is large. And you might ask, well, how can I now construct my singlet pairs? Remember, the construction before was to take opposite spins with precisely opposite momentum. Well, here, if I try to construct an opposite spin pair, you see that it will always have a momentum, regardless of how I choose it. So this was a challenge, but what these four gentlemen showed is that there isn't actually solution to this thing, and the system, nonetheless, under certain conditions, will condense. It will choose one particular momentum, Q, in real space, so it will break translation symmetry, and will form an order parameter that is now oscillating in space, and will have these kind of pairs that have now a finite momentum in space. And this state, as I mentioned, is called the FFLO or LOFF state. And nature is really unkind with these kind of unconventional superconductors. There have been only less than a handful of experiments reported claiming to have seen the FFLO state. Here I give one example of an organic superconductor where it was claimed that this FFLO state, broken translationally symmetric order parameter, appears, and as you can see, it appears just before, again, superconductivity is killed. So you apply a strong magnetic field before superconductivity is killed, the system forms this kind of triplet pairing, the FFLO state, and then it breaks down entirely. So the field was more or less stuck for a good number of decades until in the beginning of this century, people have started to look at proximity effects. So instead of looking for peculiar or unconventional superconducting states in bulk, they started looking at the effects of proximity effect, how superconductivity penetrates into a different material, and to see whether one could realize this kind of physics rather than endowing a bulk material with this property, trying to endow it from one material into another. And so the proximity effect, I'm sure you've all heard about, is a simple, relatively simple phenomena where if you have a superconductor on one side and it has some order parameter, and here I've outlined the triplet pairing. This is a triplet type of pair wave function, and I've indicated that order parameter in this conventional superconductor is 0, and I have some singlet pairing amplitude. And when I connect this system to a normal metal, what happens is that the pairs leak into the normal metal, and pair correlations develop inside the normal metal, giving rise to a finite pair amplitude in the normal metal. And of course, if the triplet pairing was to begin with 0, it will stay 0 when you put it into the normal metal. There is nothing special about this normal metal. And of course, this kind of proximity effect is going to be very useful, has been useful. It's known as the Josephson effect if you put another superconductor on the other side. And the fact that this order parameter decays if the distance between these two superconductors connected by a normal metal is short enough, you can basically revive superconductivity and you can flow a supercurrent through a normal metal, namely endowing this normal metal with superconducting properties. And note here, remember that this order parameter phase is spontaneously broken, so phi 1 is some spontaneous unknown number, but what is gauge invariant and known and controllable is the phase difference across the junction, and that will become an important parameter towards the end of the talk. And this phase difference governs the current flowing through this junction, and its maximum when this phase difference is 0, and it can be altered by changing the current through the junction or by changing the phase difference. You can think of this relation as either current controlling the phase difference or the phase difference controlling the current. But nonetheless, this entire system behaves as a good superconductor in the sense that it could flow a supercurrent without dissipation, and we've endowed this kind of normal metal with superconducting properties. And so in the beginning of this century, people asked, well, what happens if I replace my normal metal with a ferromagnet? So here is a weak ferromagnet, and you'll see what I mean by weak ferromagnet in just a second. It turns out that the fact that there is magnetic ordering in this material, there is no superconductivity there, but there is superconductivity in this normal metal, gives rise to something peculiar, and that is that the singlet order parameter decays, but in an oscillatory function way, and the triplet pairing actually develops in the ferromagnetic state and oscillates as well in a phase shift of pi. So when the singlet pairing is maximum, the triplet is 0, and vice versa. When the triplet pairing is maximum, the singlet is 0. And in fact, this spatially varying order parameter is precisely the FFLO state that I described before, now only appearing in a material that has no pairing correlations on its own, and all the pairing correlations are induced by this normal superconductor. So we've basically been able to create a unconventional superconductor that has triplet pairing by proximity. The problem with doing this experiment with real magnets is that if you increase the strength of the magnet, what happens is that the period becomes faster and the rate of decay of both order parameters becomes faster. So by the time you've ended up using a conventional ferromagnet that has really strong exchange interactions, basically you can't induce any superconductivity in this ferromagnet on any reasonable length scales. And so here the community more or less split. There were further developments in this area that use inhomogeneous ferromagnets. It turns out that if you use a magnet that is not simply polarized in one direction everywhere in space, you can somehow overcome some of these difficulties. But what I'll talk about today is a different kind of strategy which replaces this material here with a material that has no magnetism altogether, has only spin-orbit interaction, and yet will generate the FFLO state in a very, very robust manner, in a way that in fact will not depend on the strength of time reversal symmetry breaking that exists in this material. And you'll see this in just a bit. Now, so far I talked about one type of unconventional superconductor, and this is this FFLO state, the one that breaks translational order. And I'd like to talk about a different kind of unconventional superconductor that also started, more or less emerged in the past, I'd say, decade or so. And these are topological superconductors. And what you'll see is that the system that I'll describe to you, the experiments that we've done actually combine the two unconventional types of physics, the FFLO state and the one that I'll talk about now, topological superconductivity, in one system. So to get a sense of what a topological superconductor is, it's an unconventional superconductor, I'll just rely on your intuition for what a topological insulator is. And a topological insulator is one that when you look at its surface, it has surface states, as opposed to a conventional insulator that has no surface states when the chemical potential is in the bulk. So this is what we've learned. This is a single electron property. Certain materials, when you put the Fermi energy in the gap, have no state anywhere. And topological insulators are such that when the Fermi energy is in the gap in the bulk, they have states on the surface, and these are electronic states. Electrons can occupy these surface states. So in analogy to the topological insulator, let me just argue that a superconductor is a material that has a band gap in its bulk. And in fact, there are two types of superconductors. One, that when the chemical potential is in the gap, in the superconducting gap, the system has no other states anywhere else. And there are topological superconductors where, when the system is gapped in the bulk due to superconducting order, it has states at the boundaries. And these ones are topological superconductors. So to give a few examples of conventional topological insulators, here is one. That's a topological insulator, a quantum Hall state, where we know that the bulk is gapped and it has edge states on the surface, and these are in fact chiral because this system breaks time reversal symmetry. A quantum spin Hall state is another topological insulator that now satisfies times reversal symmetry, so it has two chiral states along the edge while the bulk is gapped. And in analogy with those, we have topological superconductors. And here is an example of a chiral topological superconductor. So this is now a superconductor where the bulk is gapped due to superconducting correlations, and yet the edge hosts chiral excitations. And this is a helical superconductor, one that has counterpropagating edge states. And the difference between this system and the insulating system is that the nature of these edge states are quite peculiar. So as opposed to the topological insulator where these surface states can host electrons, the topological superconductors have half the degree of freedoms that the electronic states in the insulator have. So they can host excitations that are called Majorana excitations, and they carry half the degrees of freedom of electrons. And they have some really peculiar properties that I'll just spend a few minutes describing, because partly it's these kind of peculiar excitations that we're after when we try to explore this kind of topological superconductor or unconventional superconductor. So remember, when we talked about a topological superconductor, we argued that it hosts states on its surface, but in fact, it hosts states anywhere where the gap collapses. So if I thread it with flux and the gap of the superconductor goes to 0 in the core of the flux, there we will also form these Majorana states, and because the core is 0-dimensional, these states now will become basically localized. So these kind of red-blue circles I'll call localized Majorana modes. They're basically some room to host an excitation in the system, and they could live in the middle of this vortex here. If I had a one-dimensional superconductor, the surface of that one-dimensional superconductor is here at the edge, and it can again host these kind of 0-dimensional Majorana states. And there's some properties to these excitations. As I mentioned, they're a little bit peculiar. So each pair of these Majorana localized states can host one electron state that either is occupied or not. So a pair of these can basically encode information about either a state, an electronic state, being occupied or not. And it has to do exactly with the fact that this system it's a superconductor. Normally, if a superconductor has an even number of electrons, it has a lower energy than if it had an odd number of electrons, because that odd one hasn't found a partner, so it has to pay a gap energy in order to live in it. In a topological superconductor, that's not the case, because we have these edge states, and the energy of even an odd number of electrons is exactly the same. And that's what gives this system really some interesting features, because it has a really large macroscopic ground state degeneracy that has to do with how these Majorana bound states are occupied. One of the great things that are of interest with respect to these localized Majorana states is their statistics, their quantum statistics, and it turns out that when you exchange two of those, you don't get 0 or pi as you would for fermions or bosons. You actually get something, you don't even get a phase, which is what you get for anyons, like fractional charges and quantum Hall states. You actually get a different wave function, and it has to do exactly with the fact that as you braid these two things, the underlying occupation of this state goes from 0 electrons to an odd number of electrons back to 0 as you're braiding. So basically you're getting a different quantum mechanical state, and this is what's known as non-abelian statistics. And the motivation for exploring non-abelian statistics is, first of all, fundamental physics, but of course also the possibility to encode information. So here, just very briefly, because I'm not going to talk much more about topological quantum computing, but the idea here is that each pair of these localized Majoranas encodes two states, and so the degeneracy of the system has to do with, it increases as 2 to the power n over 2, n being the number of Majoranas. And the nice thing about them is that the underlying state that's encoded by each one of these Majoranas does not change due to small perturbations, but in fact only changes when you do non-local perturbations, and therefore is very well protected. So that's the motivation. Whether that's going to be realized or not is a different story, but that's some of the interesting aspects of topological superconductors, that they can host these non-abelian excitations, and we're interested in exploring them. Now, very similar to the FFLO state that I talked about earlier, topological superconductors also are rare in nature. It's very hard to find topological superconductors. In fact, I'm familiar with only 2 or 3 examples, and I've listed here 2 of them. One is what is believed to be a state in a fractional quantum Hall state. One particular, or there are a couple of fractional quantum Hall states that are believed to have this kind of non-abelian property that will basically have to do with condensation of elementary excitations. They have fractional charges given by E over 4. In fact, we measured this charge to be E over 4, but that's not sufficient to convince ourselves that this is a non-abelian state. It's a required condition, but it's not sufficient. So this could be a candidate of a bulk system that is a topological superconductor. Another possible example, and there's a lot of debate about this, is strontium ruthenate that will have this kind of order, and again, very debatable. So just like there was a solution with the FFLO state looking at hybrid devices, it turns out that if one considers hybrid devices, one can again consider realize topological superconductors from constituents that have no topology associated with them whatsoever. And what I'd like to argue is that if you take just conventional materials, conventional superconductors, conventional magnets, and some conventional materials, for example, this is just a material that has some spin-orbit interaction in it, semiconductor with spin-orbit interaction. You could also put into the mix topological insulators. These are materials that we understand fairly well, and they're also materials that we can predict very well, so we know which material has this property or not, but they're not essential even for what I'm going to talk about. And if you create hybrids, just like this proximity effect that I was describing before, for example, if you hybridize a topological superconductor, a magnet, and one of these topological insulators, you can realize a system that has chiral Majorana modes at its boundaries. And in fact, there was a beautiful recent experiment from UCLA that argues to have seen these chiral Majorana modes in this kind of hybrid device. And note, this particular system has a topological insulator, so one ingredient is topological, and yet it created a topological superconductor where the superconductor to begin with had no topology in it. What I'll be talking about today is even a simpler system. It's just a hybrid between a superconductor and a material that has spin-orbit interaction. This hybrid has nothing topological in it, and yet I'll show that in this kind of hybrids we can realize both unconventional superconductivity due to the FFLO type, triplet pairing, as well as realize a situation where we have topological superconductivity with non-abelian particles. So what's the system? The system actually is a very, very simple one, as I mentioned before. It's just a Josephson junction. It's shown here. There is a superconductor, another superconductor, and in between there is material that has strong spin-orbit interaction. And the specific material that we have explored up to now has been mercury telluride. There have been a variety of good reasons to use that material, but in fact now we're collaborating with Javad, trying to realize the same kind of experiments that I'll describe in a system where we replace the mercury telluride, the semiconductor, with indium arsenide, yet another conventional semiconductor that just has some nice spin-orbit properties that are useful for this physics. The experiment that we're going to do is a very simple experiment. We're just going to send some current across this device and measure the critical current. In fact, that's just see how big the critical current is. And the 2 knobs that we're going to vary is one, the primary one, is going to be a magnetic field in the plane. So it's not an orbital effect. It's just a magnetic field that breaks time reversal symmetry. This is essential. And the other later on would be a phase difference. If you recall, Josephson junction cares about the phase difference between the 2 superconductors, and that will be another knob that will vary later on. So here's a schematic of this junction. There's one superconductor, another one, and in the middle here we have our semiconductor. Dimensions here are a few microns along the junction and a few hundred nanometers across. And here you can see what normally you would find when you apply a magnetic field perpendicular to a Josephson junction, and that's a Fraunhofer pattern. This is a very canonical type of pattern where the critical current shown here in this envelope is oscillating as a function of flux. And this is a magnetic field now applied perpendicular to the junction just as a means to characterize what the junction is doing. So this is going to be a very weak field on the order of a few millitesla. The big parameter that's going to change the physics is when we apply a large magnetic field on a scale of a Tesla in the plane. So remember, just to distinguish, this is a weak probing field, and the relevant parameter will be the one applied in plane. Be parallel here. Now, instead of looking at the full Fraunhofer pattern, we could just look at the resistivity. If you look at this bottom line at zero magnetic field and you ask, well, what is the resistance of this junction when we send a little bit of current? We see the resistance is zero at the nodes, at the humps here. That's where the system is superconducting, and it becomes normal every time we hit one of these nodes. So that's the characteristics of a normal Josephson junction, and we're just going to follow these nodes as a function of this parallel magnetic field. And you see for the first half Tesla, nothing much is happening, but eventually the magnetic field kills it. And first we thought, oh, this could just be we're killing superconductivity in our leads. This is aluminum, we're applying 1 Tesla. It turns out that we're not killing superconductivity in the leads, and if you increase the magnetic field further, the pattern wants to revive. And you'll see a little bit nicer data in just a minute, but the point is that there's something going on in this system where the Fraunhofer pattern entirely disappears and then reappears again. And we were really puzzled by this for a long time, scratching our heads. What is the origin of this physics? And so the first thing we did is really just to characterize it properly. So here is a map as a function of this magnetic field that I shown before, and for different densities in the junction. And the density is just controlled easily by an external gate. So we're going to look at the zero flux line here, and we're going to plot these slices. So if you look at this slice here, it's blue, it's zero resistance, then it becomes resistive, and then it becomes lower resistance again. And we're going to do it for each one of these points on this map, and we get what I call a phase diagram. This phase diagram tells us where the system is superconducting as a function of the magnetic field in plane and density. And we see a big, big blue C here in the middle. So this is the normal behavior. And the way we construct it, by the way, is taking all these Fraunhofer patterns for each one of these conditions. But we see 3 regions here. One here that I already mentioned. There's another one here. And there's another one at very low densities that I'm not going to talk about. So forget about this one. It will require me some more time to explain where this one is coming from, but I'm going to focus on these two, and I'm going to argue that these are exactly these kind of FFLO states that I mentioned before. So let's see, what do we expect? So here's our semiconductor. It's a very simple semiconductor. It's two-dimensional, so the Fermi surface are 2 circles. And it has a particular type of spin orbit known as Rashba spin orbit, or basically it breaks inversion symmetry. And the way the spins in this Fermi surfaces are aligned is you see that the inner Fermi surface, the spins are going clockwise, and in the outer Fermi surface, they're counterclockwise. The spins are in the plane. But nonetheless, they are, so this is not the Fermi surface of the ferromagnet that you remember I mentioned before. That would be the case where the spins in the Fermi surface in the inner one all pointing in the same direction, and in the outer one pointing all in the opposite direction. So here they're chiral, they're circling around, and it's a simple outcome of spin-orbit interaction known as Rashba spin-orbit interaction. Now there is something very nice about the way spins are aligned in this system, and that is that it's very easy to form a singlet in the way that we really wanted it, right? Opposite spins, spin up here, spin down here, and opposite momentum. So this system is just like the normal system without spin-orbit interaction, it's very happy forming singlets and creating a normal S-type superconductor. No FFLO state will appear here because each pair here has zero momentum and can easily form a singlet. So that system is very happy. But now the question is, what happens when we apply the in-plane magnetic field? That's the variable that changes the physics. And it's not very hard to see. One could derive it in a few minutes on a piece of paper, that when the magnetic field is applied, what happens is that one Fermi surface shifts relative to the other in a direction that's perpendicular to the applied field. Intuitively, you could see why. The spins that are on the north and south pole are pointing perpendicular to the magnetic field. So their energy is not going to change. And you see that this energy difference, therefore, this splitting in momentum space is not varying for the spins that are perpendicular to the magnetic field. But the spins that are along the magnetic field, either parallel or anti-parallel, the ones that are parallel gain energy, so they go down in energy. The ones that are anti-parallel lose energy, they go up in energy, so the distance in the Fermi surface between these spins grows. And the end result is just this shift in the two Fermi surfaces. So now we can look at what happened to our pair wave function. If we look at the pairs that we had before, an up and a down on the inner Fermi surface and a down and an up on the other one, you see that now each one of these pairs acquires a momentum. And the momentum is only in the direction perpendicular to the magnetic field. And if I just write this pair wave function in terms of a cosine times a singlet and a sine times a triplet, you can easily see that depending on the value of magnetic field, which controls this shift in momentum, and depending on how far these pairs have to propagate, I will get exactly my oscillating order parameter, where when the distance between the two superconductors is very small, I get a pure singlet. But at large distances or for large magnetic fields such that delta k times w is pi over 2, I get a pure triplet. So suddenly I have a knob in my system where I can control the order of the pairs from singlets to triplets. And in fact, in real space, you'll see a plot of this in just a minute. You will see that we have this kind of FFLO state building up. Now, there is something very, very unique about inducing this particular order parameter in this geometry. Note, here I've considered a trajectory of this pair wave function going directly in the shortest path from point x1 to point x2. But what if I were to consider a different path? Would the phase be different? Well, it turns out that it won't. And the reason is that the momentum that these pairs acquire is only along one direction. So it's only the direction along this x-axis that matters. And so if I sum over all quantum mechanical trajectories and look at what is the net result of my order parameter, it's exactly the same. So this is very, very robust. And if you just simulate this kind of system with this in-plane magnetic field, you generate exactly this node. And note, now we understand why there is a node. At this particular value of magnetic field for a fixed junction, for a given junction, what happens is that all the pairs that leave one superconductor, they left as a singlet, they arrive on the other side as triplets. If they arrive on the other side as triplets, they can't enter the aluminum. The aluminum only welcomes singlets. It's a singlet superconductor, and the supercurrent goes to 0. So this node is a condition where we've created a filter. We are basically filtering out all pairs. None of them can go through, and the system is purely triplet. In fact, if you increase the magnetic field a little bit, note that the singlet order parameter will come back on, but it will have an opposite sign, and this will be important in the 1 or 2 slides before the end. So just remember that this condition here is really a very nice proof that we have triplet pairing in this system, and beyond that, the system has a phase difference of pi because the singlet order parameter changes sign. Now, I've talked about what happens in this corner here, where we said this is exactly triplet pairing, and here we change the order parameter. What about this lobe here, this region here? And it turns out that the Fraunhofer pattern actually here looks quite different. It doesn't simply vanish at a particular magnetic field. It actually some of the side lobes converge in, only the center lobe vanishes. And it turns out that the physics associated with this behavior is precisely that of the ferromagnet. So let's consider our initial FFLO situation, where now we have all the spins in the inner Fermi surface pointing down and all the spins in the outer Fermi surface pointing up. So this is an itinerant ferromagnet. And again, as the FFLO guys argued, this system has a finite momentum in any direction you choose. And if you write down the induced order parameter, you see that now you again acquire these phases. Only now this phase is the same in any direction you look. And so if you choose a longer trajectory, you're going to get a longer path. So all the trajectories now, all these quantum mechanical paths interfere, some destructively, some constructively, and the end result is exactly what we see in experiment, where now some of the side lobes converge, and this in principle will repeat at higher and higher magnetic fields, but this is a physics associated with strong magnetic field and very weak spin orbit. So it's a very controllable system, and the robustness of this particular phase is that in principle, you see that the order parameter as you go to higher and higher field doesn't decay. This one suffers from what the FFLO guys argued to begin with, is that as you increase magnetic field, the entire order gets suppressed. It doesn't happen here. Experimentally it does, and we have some ideas why, but in principle it shouldn't. Okay, so just to give you a sense of how this order parameter looks in space to connect with the original FFLO picture, so here is the induced case for the spin orbit case where you see the order parameter oscillate, and depending on where the size of your device is or the strength of the magnetic field, it basically controls the period of this oscillating order parameter. You can get pure singlets or pure triplets or anything in between. And this is what happens when you have this kind of itinerant ferromagnetic case. You see that the order parameter actually oscillates both away from the superconductor but also along it. And we're designing experiments to see this kind of oscillation perpendicular to the normal. All right. So far, I've talked about the FFLO aspect of unconventional superconductor. Now I'd like to argue that in the same geometry, the system actually has properties of a topological superconductor, and it can host these Majorana excitations. So here's a schematic of what we're studying. It's basically a superconductor, another superconductor, and some material that has spin-orbit interaction. The ingredients have not changed. Up to now, we've just considered what happens when we supply a magnetic field along this direction, and now I add this other variable of a phase difference across the two sides. It turns out, and I don't want to go through the math, it's actually not a very complicated model to solve, but you can write down and ask, well, under what conditions does this system altogether become a topological superconductor? I'm just giving you here the results as a function of the two key parameters that govern this system. One is the magnetic field, and the other is the phase difference. And what you see is that these green patches that are denoted by T, these are topological phases. So this is, everywhere in the green, the system is actually a topological superconductor rather than a normal superconductor. In the entire phase diagram, except for the phase boundaries, the system has a superconducting gap. But in the topological phase, this gap, the system has end states, shown by these gammas here, and in the normal state, it doesn't. And these gammas are exactly these localized Majoranas that reside at the boundary of this device. So this is really a cool thing. We don't know how to predict superconductors at all. If you give me a material composition, I can't tell you whether it will become superconducting. Yet, if you give me a superconductor that you know it's a superconductor, and you construct something like that, I can predict that it will become a topological superconductor. So this is really powerful. And the other thing that's really powerful here is that it's a switch. I can switch the phase across the superconductor really fast, so I can go from a normal to a topological superconductor at will. I just flip the switch here and change the phase, and I will go from one to the other. The other thing to note is that when the phase difference across these two superconductors is pi, the system is in fact always topological. So it's very robust. Moreover, I didn't specify anything about the property of this two-dimensional system. In fact, this phase diagram is independent of what the density of electrons in this semiconductor is. It's independent. I can choose the magnetic field, but you see that for every magnetic field I have a topological phase, and in fact is independent of the distance between the two superconductors. What these quantities determine is the size of the gap, but not the topology, whether it's topological or not. So here, just to give you a sense, this is a map, a color map of the size of the gap. Anywhere that it's yellow, it's close to the gap of the underlying superconductor that hosts, that proximatizes this geometry. But you see that in this side, within this diamond, I get a gap that's comparable to the superconducting gap. So I can get fairly large gaps. And of course, when the system undergoes the phase transition from normal to topological, the gap disappears. So we expect to have fairly large superconducting gaps here. And these superconducting gaps are expected to host these topological excitations that are situated here. So first, I'd like to argue that, in fact, we've already seen the transition to the topological phase. And the reason is, remember, when we cross this boundary here, I mentioned that the order parameter changes sign. And in fact, in this region here, the junction has a phase difference of pi. That's its ground state. So whereas, remember, when we discussed the Josephson junction to begin with, I said the maximum critical current appears when the phase difference is 0. Here, once you cross this boundary, the system actually wants to have a phase difference of pi, and you can even convince yourself experimentally that the phase difference of pi is pi by doing an interference experiment, which we've done. So the phase difference is in fact pi, and remember, when the phase difference is pi, the system is always topological. So we believe that this corner of the phase diagram is in fact entirely in the topological phase, and at the boundaries here, these Majorana states need to reside. And currently, we're running experiments to try to detect their signatures, and these could be done by tunneling experiments, for example. And here's just a theoretical calculation showing the difference between the tunneling spectra at the edge, whether it's normal or topological, you get an additional state that resides at 0 energy. So these states will have a very specific characteristic that we're interested in finding. And so here are some of the designs. I don't want to go into that. So in the last minute or two, I just like to give a little bit of an outlook of where we're headed, or some of the interesting features of this system. So as I mentioned to you, first of all, there aren't many examples of unconventional superconductors with pairing order parameters that are non-singlet, but suppose there was one, how would I know? So how would I probe a superconductor to tell me, oh, it actually has triplet pairing? And I'd like to argue that this kind of interference geometry that we've devised is a perfect way to probe where the system has triplet pairing. Imagine I construct a device out of my choice of superconductor here, let's say aluminum, my spin orbit material here, and here an unknown material. We already saw that if this unknown material here has singlet pairing, we'll get this kind of feature when we apply the magnetic field, because when we start at 0 magnetic field, singlets leave this superconductor and arrive in the other one and are happy to go in. So we have a maximum critical current, and when we convert them to triplet, the current goes to 0. But if this material was triplet to begin with, then at already 0 magnetic field, we won't see any critical current because we won't be able to send any singlets into this p-type superconductor, and yet the current will then turn on once we apply magnetic field as we're slowly converting our singlets to triplets, and suddenly current will flow. So just by looking at this kind of map, we should be able to say something intelligent about the ordering of this target superconductor. Now, p-type superconductors have 3 flavors that could be an m equals 0 triplet, +1 or -1. It turns out that there are games, and I'm not going to describe them here, but in which one could actually even attempt to distinguish between the 3 types of ordering that could be in this material. So this is an exciting thing to try, basically probe materials with unknown order through this kind of interference device. With this, I'd like to just acknowledge who's contributed to this work. So primarily, it's this triplet pair. Sean Hart, Hetchen Ren, and Michael Kosowski have really nailed down these experiments over several years. And we've benefited from beautiful collaboration with Lawrence Mollenkamp, who's provided us with the samples, and a lot of theory insight from Bert Halpern. Thank you.
Any questions?
I'm wondering how you tunnel it and find out into edge states. Do you have to do that? Can you do that in the planar geometry? I mean, you want to find out if these are where the
Yeah, so you can definitely do it in a planar geometry. Here's an example where if the green is your two-dimensional electron system that you formed it into a mesa, so it's etched everywhere else, you see we've left here a little bit of a weak link, and you can even gate this weak link so that you're controlling the conductance, so you can tunnel to this edge. This is one example. You can try to put a metal that makes a poor contact through an oxide onto the edge. So we're trying different things. In particular, this geometry is very amenable using indium arsenide material, and hence our very nice collaboration with Javad. Paul?
In your picture with the oscillations, is that a cartoon or is that data?
No, that's a cartoon.
You would supposedly do it by tunneling, by scanning.
Yes, you could, which will not be easy. I would argue that the data is also the oscillation, but instead of changing the distance between the electrodes, we're changing the period with a magnetic field, right? So for a fixed distance, you see so basically let's see, let's go back to some data.
But the way you do the edge is by scanning, right?
Yeah, if you wanted to see this thing in real space, you would either need to design a system with different dimensions, or you could scan and look at the order parameter in the system by doing that. But this is in fact an oscillation in, if you like, in momentum space for a fixed dimension. Yeah.
I guess in the FFLO state you don't see very clear Fraunhofer pattern. If I saw that.
In the higher magnetic field. Yeah.
Is there a reason that gets washed out in that state?
Yeah, so I focused only on the experiments in aluminum. We've done the same experiments with niobium where you do see very nice Fraunhofer patterns at higher magnetic field. There's a little bit of other jittery that takes place. It's not entirely clear to us why the physics, the intensity of the critical current dies off as you increase magnetic field. In this geometry, theory tells you if your geometry is perfect, you should get no decay. What we believe has to do with something that's related to a Doppler effect. If the edges of your superconductors are a little bit rough, on the nanometer scale, not something that you're doing deliberately, but just your conventional lithography does that. When you put a magnetic field in this direction, right? If your edge is rough, your magnetic field lines will go up and down, which means that they're giving you some random phases into the junction. And as the magnetic field increases, the size of these random phases will increase and will scramble the interference. So we believe it has to do with that. So if we could produce more perfect junctions, I think this will improve, but this is our hunch. But yes, with niobium contact, we can in fact see 1, 2, 3 of these nodes consecutively, not only one.
Can you eliminate the magnetic field? That's what I mean. This is probably not so convenient to have a Tesla-like field.
Yeah, we can put one of your magnetic layers on top, and it will produce a static magnetic field. And you need to break time reversal symmetry.
But it has to be that elongated.
So actually, it doesn't. There is an so there are some other spurious effects that will arise when you apply the magnetic field in the other direction. But if you could eliminate them, and I haven't told you what they are, but suppose they're not there. I've described what happens when the spin-orbit interaction is Rashba. If the spin-orbit interaction is Dresselhaus, it's bulk inversion, asymmetry, then it turns out that you have a control. You can, in fact, choose how you design your device such that this physics arises when you apply the magnetic field along the channel or perpendicular. You just need to choose the orientation relative to the crystallographic orientation, and you will be able to select that. Yeah, so there are a lot of knobs that can go in. Yeah. Yeah.
Sorry, I am not an expert on the field. Is this method to create topological
Superconductor. Of course. No. So this is our favorite method of choice. There are other people who are trying to induce topological superconductivity in one-dimensional systems. There are ways to do it also on the surface of a topological insulator. The surface state of a bulk topological insulator has the desired properties such that if you proximitize it with a superconductor, it will become a topological insulator. So there are actually quite a few. All of these are basically hybrid type of devices. We have no protocol for generating a bulk topological superconductor. So all these ideas are hybrid devices. What I like particularly about this two-dimensional system is, we talked about braiding. But this kind of phase transition, if you ask, well, what happens to these Majoranas as you cross this transition from the normal to the topological one or vice versa? What happens actually is that they fuse. So you can use this kind of knob of changing the phase, and we've began to think theoretically how would one do that to controllably braid. You need to move these Majoranas in space in order to achieve the kind of computation, if you like, associated with the non-abelian statistics. And this kind of phase diagram really allows you a nice knob to do it, which is much harder to do if you're confined to one dimension. So there are some nice features, but it's by no means the only way.